Hello, this is a presentation about the ion carbide phase diagram. We will talk about phases present, invariant reactions, and slow cooling of plain carbon steels. This is the diagram. This diagram is applicable to plain carbon steels. Those are steels that contain from 0.03 to about 1.2 weight% carbon, and they also contain from 0.25 to 1 weight% manganese and other impurities that are added for strengthening. The phase diagram shows on the horizontal axis the weight% carbon from 0 up to 6.67 weight% carbon. And on the vertical axis, it shows the temperature. One of the most important phases is alpha ferrite, that is shown here in this very small region on the left side of the phase diagram. Alpha is an interstitial solid solution of carbon in alpha ion. If you remember, ion has a BCC structure up to 912 degrees Celsius, and we can dissolve carbon interstitially in that structure. But alpha has a very low solubility for carbon. It can dissolve a maximum of 0.02 weight% carbon at 723 degrees, as shown at this point on the phase diagram. And the solubility decreases at lower temperature. For example, at 0 degrees Celsius, the solubility is only 0.05 weight% carbon. Another important phase is austenite, also named gamma austenite. It is an interstitial solid solution of carbon in gamma ion, that is FCC. It has a face center cubic structure. Gamma can dissolve more carbon, up to 2.08% carbon at a temperature of 1148 degrees Celsius, as shown at this point on the diagram. At 723 degrees Celsius, gamma can dissolve 0.8 weight% carbon. Another phase is delta. This is less important, but it's still good to mention it. Delta is a high temperature phase, a solid solution of carbon in BCC ion. If you remember, BCC ion exists between 1394 degrees Celsius up to the melting point of ion at 1538 degrees Celsius. Delta can dissolve up to 0.09 weight% carbon at a temperature of 1495 degrees Celsius. Very importantly, the phase diagram shows the intermetallic compound iron carbide, that is also named cementite. The chemical composition is iron 3 carbon. By weight, cementite contains 6.67 weight% carbon and 93.33 weight% iron. The atomic percentages are 25% carbon and 75% iron. Then we can observe other features on the diagram. At high temperature, the iron mixed with carbon is in a liquid phase. In this region of the phase diagram between the liquid and gamma austenite, we observe a mixed region of liquid and gamma. On the right hand side at high temperature, we observe liquid and iron carbide and cementite. Below the temperature of 1148 degrees Celsius, in this region we observe austenite, gamma, and cementite, iron carbide. Whereas below 723 degrees Celsius, we observe a mixture of alpha ferrite, and cementite, that is iron carbide. Several important invariant reactions can be observed on the diagram. One is the peritectic reaction. In a peritectic reaction, a liquid phase reacts with a solid phase to obtain a different solid phase on cooling. For example, on the iron-iron carbide phase diagram, liquid with 0.53 weight% carbon reacts with the delta phase containing 0.09 weight% carbon at cooling through 1495 degrees Celsius. And the phase that is obtained is gamma, is austenite with 0.17 weight% carbon. We can notice this on this little portion of the phase diagram. This tie line, this horizontal line, is at the temperature of 1495 degrees Celsius. And in this small region of the phase diagram, liquid coexists with delta. Right below this point, we observe gamma phase or austenite. So delta with 0.09 weight% carbon reacts with liquid that has 0.53 weight% carbon on cooling through 1495 degrees Celsius, on cooling through this point, and the phase obtained is gamma with 0.17% carbon. Another important reaction is the eutectic reaction. In a eutectic reaction, liquid is converted into two different solid phases on cooling through the eutectic temperature. And we notice that liquid with 4.3 weight% carbon on cooling through 1148 degrees Celsius is transformed in a mixture of gamma, austenite, and iron carbide. Gamma has 2.08 weight% carbon, and austenite has the fixed composition of 6.67 weight% carbon. One of the most important reactions is the eutectoid reaction. In a eutectoid reaction, a solid phase transforms into different solid phase on cooling through the eutectoid temperature. The eutectoid point for the iron carbide phase diagram is at 0.8 weight% carbon and 723 degrees Celsius. Gamma austenite with this composition of 0.8 weight% carbon on cooling to 723 degrees Celsius becomes a eutectoid mixture of alpha and iron carbide. The alpha in the eutectoid mixture has a weight% of 0.02 carbon, whereas iron carbide has 6.67 weight% carbon. We classify the steels using this eutectoid point. Steel with 0.8 weight% carbon is named eutectoid steel. With less than 0.8 weight% carbon is named hypoeutectoid steel. And with more than 0.8 weight% carbon is named hypereutectoid steel. This classification is very important, especially when we discuss the slow cooling of plain carbon steels. If the eutectoid steel is heated to a temperature in this gamma region, let's say 750 degrees Celsius, and is held at 750 degrees Celsius for a sufficient time, the structure will become homogeneous austenite as shown by this circle. We observe the grains of gamma, the grains of austenite. These thin lines are the grain boundaries. As it is cooled through the eutectoid temperature at 723 degrees Celsius, gamma is converted in a layered structure of alpha and iron carbide. We observe this structure on the right. We observe the layers of alpha and iron carbide. This structure is named pearlite. Note that very often iron carbide is called cementite. We could say that pearlite is made of layers of alpha ferrite and cementite. Let's consider the slow cooling of a hypoeutectoid steel. For example, a sample of 0.4 weight% carbon that's initially heated to about 900 degrees Celsius and held for enough time so that it is austenitized, so that the sample becomes homogeneous austenite, homogeneous gamma. As the sample is cooled, it will enter this region of the phase diagram, and alpha, proeutectoid alpha, starts to form. And we observe the proeutectoid alpha at the grain boundaries of gamma. These little blobs are proeutectoid alpha. As the temperature is decreased, the amount of proeutectoid alpha increases, as we observed on this little structure. The maximum amount of proeutectoid alpha is right above 723 degrees, right above the eutectoid temperature. Right above 723 degrees, alpha has a composition of 0.02 weight% carbon, whereas the gamma, the austenite, has a composition of 0.8 weight% carbon, the eutectoid composition. On further cooling to 723 degrees, gamma of the eutectoid composition is converted into perlite. Therefore, the structure below 723 consists of proeutectoid alpha and perlite. You remember perlite is made of layers of alpha ferrite and cementite, iron carbide. This can be observed on the right. This is perlite, layered structure of ferrite and cementite. And this is the proeutectoid alpha that is formed above 723 degrees. Next, let's consider the slow cooling of a hypereutectoid plain carbon steel. For example, a steel that contains 1.2 weight% carbon. The steel is initially heated to about 950 degrees Celsius in this region, the gamma region of the phase diagram, and it is held for sufficient time so that it's austenitized. As it is cooled and this solvus line is crossed, iron carbide starts to form at the grain boundaries of gamma. Recall please that iron carbide is also named cementite because it looks like cement that binds the grains of gamma. As the sample is further cooled, the amount of cementite increases. Right above 723 degrees, gamma has eutectoid composition of 0.8 weight% carbon. And on further cooling, on cooling to right below 723 degrees, gamma is converted into perlite. Therefore, below the eutectoid temperature, the structure, the microstructure consists of perlite and proeutectoid cementite or proeutectoid iron carbide. This is shown on this picture on the right. This is the perlite that resulted from gamma, the cooling of gamma, and this is the proeutectoid cementite, the proeutectoid iron carbide. Thank you for watching.